that way. And when you know how to write shared memory, we'll do the same thing where the child can store the values that it has computed in the shared piece so that the parent can read. So in that way, the same assignment will be then repeated in different forms. Okay, so let's focus on today's class. Okay, so when we talk about the types of scheduling scenarios, there can be different cases. One is the uniprocessor scheduling, multiprocessor scheduling, and real-time scheduling. So these are the different scenarios where we know the scheduling algorithms need to be used. Uniprocessor means where we have got a single CPU, physical CPU, and there are multiple processes which are competing for getting the CPU. So typically that is the situation, and our main focus or discussion in this class will be mainly focused on that uniprocessor kind of scheduling. Multiprocessor scheduling is whenever you have got a quad say core or maybe dual core, you have got multiple CPUs, then definitely you have got more than one CPU, so multiple processes are there. So there might be some other issues which will say that it's not that the top four process in the ready queue will be just passed on into in the four CPU processors that are having in a quad core, or it may not be just the top two process in the ready queue will be passed in a dual core. There might be other issues also, because these two processes, when they run simultaneously, they might depend on each other. They might try to interact with each other, and that also might be a criteria. So whether we pick up two processes which are highly interacting with each other or they are not interacting with each other. So these might be the issues which may be significant in a multiprocessor kind of scheduling. So we are not going into details of that. Real-time scheduling, while in the introductory, talking about the introductory classes, we found that this real-time scheduling is meant for real-time systems where deadlines are given and the process need to complete things within a given deadline, and if it is hard it must do it, otherwise the whole system collapses, like that. So it's basically deadline based scheduling. Okay, but typically when we talk about scheduling in operating system, we focus on, or we mainly mean the, okay, just a minute, we basically mean the uniprocessor scheduling. Just a minute. And in this uniprocessor scheduling, I think that day the class last week, director's class, it was he could not take the class because of technical problems. So what he was talking about is the requirement of scheduling in different situations in a uniprocessor system. So when you require some kind of scheduling, so now when we talk about scheduling, we talk in a very broader sense. So scheduling, when it is required, there are different situations when it is required, even in a uniprocessor scheduling. If you say recall the state transition diagram, which was something like this, there is a this is a CPU running state, user running state, is a kernel running state, and this is the ready state. Okay, so this is the this is a ready state, this is a swapped out, this is a swapped state, this is a swapped out state, like this. So that was the typical, I think you can recall that. Okay, so there are certain, and this is a preempted state was here. Okay, and these are zombie state, like this. So Z, this is running, and this is when it is created. So it is just created, it becomes in the ready queue, so it is created. Okay, so this is the kernel running and this is the user running, and these are swapped in and these are swapped out. These two are the swapped out states. So swapped out what? Swapped out in the primary in the secondary memory, swapped out. I think many of you can recall it. Okay, this is swap team. So the point is, if I look into the state transition diagram right from the beginning, so when you are trying to create a process, it might happen that there is not enough resources in terms of memory or in terms of process control block entries. I mean process table entries and all this. So even though you write, say for example, you press dot slash a dot out, you press an enter, but you might find that your process is not created actually. So created means you request the process to be created through this execution, but the process is not getting created because there is not enough memory or not enough resource in the system. So uh, so here there is a decision need to be taken by the operating system. So whether a process creation request can be actually uh, mm, it can be satisfied. Okay, so this is a, so this decision is taken through a scheduling algorithm, and this scheduling is, as you can feel, that it is not quite often it will be invoked because this resource is becoming too scarce, the memory is almost full, or the process tables are almost full. So these are very very rare. So that's why this is often called as a long term scheduling. Long term means decision when a new process waiting to be created is actually created. Okay, is the uh, recording on? Every time I, okay, it is on. So some of you please note that the recording is on every time I start the class. Okay, so, I often forget to do it, and there are a lot of recording issues that I am facing these days. So this is the decision when a new process waiting is to be created. So this is a long term scheduling. In the medium term, so medium term and the short term scheduling. So the medium term is related to uh, not CPU, but when a process is suspended or blocked. So instead of keeping them in RAM, those processes might be swapped out of the primary memory and may be placed in the secondary, because they are in no way they are going to compete for the CPU. So these decisions, so when this decision will be taken when we find that the RAM is not having enough number of frames to accommodate new pages of the ready or say running processes. So this is a decision that entirely related to the memory management module, and this decision is all about whether to swap in or out some of the processes which are in the suspended state or maybe in the ready state also. So as we found that in that from the ready state also things may be swapped out often. So this is a decision that is more frequently taken compared to the long term scheduling because it is related to memory, and often you will have some situation such situations. Okay, but the last one is the most important one, which is of our interest. This is a short term scheduling. All it says that in the ready queue, if you have got the ready queue here, so all the processes are waiting in the ready queue, which are created, which are preempted maybe. So this in the ready queue, all the processes which are waiting for the CPU, there should be some algorithm which will pick up one process from the ready queue and will assign it to the CPU. So this it is not trivial because it is not just a queue whose first process is the process which joined the queue first will be actually assigned the CPU. So this is also an option which is basically known as first come first serve, FCFS. Whichever process joined the queue first will be uh, scheduled first to the CPU. So although there is a notion of ready queue, but the scheduling of the processes from the ready queue to the CPU may not be always FCFS based. Okay, so there are other and many other possibilities or possible algorithms which we can plug in here, and that is all about the short-term scheduling, because the decision in this case is quite frequent, at least in a time shared system. In a time shared system, you all know that it is based on a timer which ticks, and the time quantum of the timer is typically very very low, very small value in the order of milliseconds or nanoseconds maybe. So as you can feel that every nanoseconds after every time quantum, the running process will be preempted, will be forcefully taken out the CPU, and the scheduling algorithm will be activated, which will be based on the parameters, different parameters of these ready processes, it will schedule one process, pick up one process for scheduling. So the frequency in which this scheduling algorithm is executed is the highest. It's almost like every nanoseconds or every few nanoseconds this scheduling algorithm is executed. So that's why it is called short-term scheduling. So it's very frequent. And because of this, the design of this algorithm is very critical in terms of the performance of the operating system. Or in other words, you can always think of very sophisticated algorithms which might take a number of parameters, and it can do nice things, but in reality you cannot really use those algorithms, because if the scheduling algorithm takes too much of time to find out which process next, then what the process is, so it will just eat up a lot of CPU time. So that's why these short-term scheduling algorithms need to be lightweight and yet effective. Okay, so what are the design parameters while such a scheduling algorithm is designed? So there are many, as I mentioned, there are many possibilities, and we'll look into, so these are the possible algorithms. We'll look into these algorithms, but the design parameters that you should consider before actually implementing one of those algorithms in your operating system design. So to do that, these are the design parameters. So one is so there are different parameters which are broadly classified as say, which is based on the user's perspective and which is based on the system's perspective. So user's perspective means those parameters are trying to maximize, or optimize some of the some of the parameters which is of interest to the specific user. So, and then again, and the other part is consists of parameters where it is from the system's perspective. So the overall system's performance is affected or it is optimized. And in each of these two, we have got performance based, which you can really quantify, which you can calculate, and one is non-performance based, which is qualitative nature, which you can say it's good, bad, or like this. You cannot precisely quantify it. Same in case of systems perspective, you have got the set of parameters into two types: performance based and non-performance based. So if we look into these parameters, these are many of them are well known to us: turnaround time, response time, and deadline. So turnaround time, we know it's the amount of time to execute a particular process, means once it joins the system till the point it completes, and in between it might use the CPU in multiple multiple phases, or multiple bursts. Sometimes it uses CPU, sometimes it waits for the CPU in the ready queue, sometimes it goes for the in the blocked state and all this. So during its entire lifetime, so it's basically the entire lifetime of the process, it's a turnaround time. So which comprises of its service time, the amount of time it utilizes CPU in multiple bursts, its waiting time in multiple instances, and also its waiting time includes ready queue and also suspended case. Response time, this is the amount of time it takes from when a request was submitted until the first response is produced. So this is typically in case of an interactive time sharing environment, as we all know. So no matter what the process is doing, a dot out or whatever, so it might ask for input and you provide the input, it provides some output, again it asks for input, you provide some output, so it goes on. So the entire execution of that process, executable a dot out, this might take maybe 5 minutes, but in between you might interact multiple times, and each of the response during that interaction matters. So obviously the the user expects the response time should be very, very less. Turnaround time also should be very, very less. So these need to be minimized, and these are what the user expects. So the user perspective. The deadlines are also something that is related to the real-time real-time scheduling strategies. Now the non-performance based, it's a qualitative nature, it's a predictability. Now think of the case that there are say 5 users currently logged on in a server, Unix server or Linux server, and then one of them is executing a very computation intensive code. It's a simulation code, so no interaction, almost no interaction. and 4 of them they are basically trying to do some kind of interactive menu based programs. So the thing is, and you want that things should be very much predictable. So the predictability means your response time or turnaround time should be should not depend on the load of the system, should not depend on what type of processes are running, CPU bound or IO bound. And or I mean, it should be predictable. So it should not happen that in the morning hours if you run a code it takes just 2 minutes. In the evening hours, in the rush hours where too many users are logged in, the same code takes say maybe say 10 minutes. So then the user will feel that something went wrong in the program itself, but it's not the case. It's a scheduling strategy which created this difference. So in any case, the predictability, the performance should be predictable. So the user must know that more or less this kind of code will take this much time. So this becomes easy for the user to perceive the performance of its process also. In the system's perspective, it is the throughput, which is the measurable parameter and which is of interest to the entire system. Maybe the system administrator, he is not bothered about how a particular specific user feels about his response time or say turnaround time. Rather, he is more important to maximize the throughput of the system. So if he finds that on an average per second, say 2 or 3 processes gets completed, and even if some process which is maybe CPU bound is waiting for hours after hours, he is not bothered. He is basically interested in maximizing throughput. So from the systems, overall systems perspective, throughput is a major criteria, which can be measured in terms of the number of completions per unit time, but a particular user is not interested about the throughput. So when I am logged in the system, I don't care about what others are having the feel. So I just want to minimize my turnaround time, my response time, no matter what others are doing. So the point is the users and the systems, user and the system, often the perspective is contradictory in nature. Okay, so you cannot probably minimize this at the same time maximize this also. So this throughput maximization and minimization of response time may not be able to ensure. One may not be able to ensure simultaneously. So there is not possible to design a scheduling algorithm which will be ensuring both. So they are often contradictory. And finally, in the system's perspective, the non-performance based or qualitative parameters are fairness or balancing of resources. Fairness in the sense, so the scheduling strategy should be fair to both the IO bound and the CPU bound processes. So IO bound and CPU bound, do you all know? So CPU bound it has got long CPU bursts like this and a small bit of IO in between. So the CPU bursts are long. So these CPU bound jobs, and the IO bound jobs are short IO, short CPU bursts followed by the IO. So this is IO bound jobs and this is, so this we have already explained earlier also. It's just to, so this is IO bound and this is CPU bound. Okay, so when we consider fairness, so no matter whether it is a CPU bound or IO bound, both should be treated in a fair way. So you should not have bias towards a particular type of processes. Okay, a particular type of process. So, and balancing of resources, the scheduling algorithm should ensure that both the CPU as well as the IO are the utilization are maximized. So it should not happen that you are trying to maximize the utilization of CPU, but the IO is getting it is just sitting idle. It's not getting utilized. So that's why we often know that we prefer to have the IO bound jobs more priority, to offer more priority, so that both the CPU as well as the IO is fairly utilized. So these are such things, these two and say this one, which you cannot really quantify, but still it is important and it's a qualitative metric. Next, these are the list of the CPU scheduling strategies. So there are few of them in number. Among these I'm not going to explain it here because we'll have the details of each of them. So the point is some of these are non-preemptive nature and some of them are preemptive. So three of them are non-preemptive and the rest of them are preemptive. And preemptive, the term we already came across. Preemptive means CPU can be taken away forcefully as per scheduling demands. So a process is running, process got the CPU, it is running, and it is no way it is not really interested in releasing the CPU because it is not requiring IO, neither it is requiring any termination. But still, because of the CPU scheduling algorithm, it is forcefully, the CPU is taken out of it. So that is what is called preemption, uh, forceful deallocation of a resource, in this case CPU. But a non-preemptive strategy means once the CPU has been allocated to a process, no matter what other processes are waiting and what may be the kind of nature of those processes, the present or the current running process will not be forcefully taken out the CPU until unless it releases it voluntarily, maybe because of IO or because of termination. So if it is not releasing it, nobody is going to take out. So this is non-preemptive type. Okay, so you can see that three of them are non-preemptive type. This is FCFS, first come first serve, shortest process next or shortest job first, and it is highest response ratio next. So these are the non-preemptive type, and the rest, in fact, the scheduling algorithms that we use uh, popularly in the Linux based systems, so in the actual implementation, these are obviously preemptive type because otherwise it will be a monopolization of the CPU usage by the CPU bound jobs. Okay, and this fair share scheduling is one which is actually implemented in the Linux or Unix based systems. So this will explain in details later on. So this has got certain nice features which actually and in a very effective way and a very lightweight way, it will try to include many of the features of these queue based scheduling techniques. Okay, we'll see that later. So let us talk about the scheduling algorithms one by one. So first is the FCFS, first come first serve. As you can see this table, we show here the process names, process A, B, C, D and E. There are 5 processes that we consider, and these are the typical process related parameters that is shown here. So TA is the arrival time. So this is the time when the process A arrives in the system. It is almost at the beginning, t equals to 0. Process B arrives in the system after 2 units of time. C arrives after 4 units of time. D arrives after 6 units, like this, E after 8. And TS is the amount of CPU time required by the process uh, during its execution. So this is listed as 36452. And the point is that these things are something very uh, unnatural because a process, when you start a process, say like a.out, how a process knows, how the system knows how much time, service time, or like this TS is a service time, how much service time or CPU time will it require, so how it comes to know. But still, let us assume that hypothetically we know the service time of these processes, of all the 5 processes. But in reality, you should know that this is not easy to estimate or guess or whatever, because all it depends on your input, the type of inputs, and many other factors. Okay, so these are some values which are hypothetically known. I mean, these are known, but maybe uh, these are assumptions you can think of. Now finish time is, if you apply this strategy, then applying the strategy you should be able to know that when these processes are completed, I mean with respect to the time. And this turnaround time is the difference between the finish time and the arrival time. That's the definition that we all know. And the last one is the normalized turnaround time. That is the turnaround time which is normalized by the service time. Okay. So if you have got if your turnaround time is almost same as that of your service time, then this normalized turnaround time should be 1. So the thing is, this turnaround time in some other way you can say that this is equal to the service time plus the waiting time, as I just now mentioned, that turnaround time of a process includes its service time as well as its waiting time. And this normalized turnaround time, then it will be TR by TS. So this will be 1 plus TW by TS. You can see this one. It will be 1 plus TW by TS. So ideally, what should be the case? A process comes and nobody is there to compete, and the waiting time is 0. So in that case, it will be just 1. TR equals to normalized turnaround time equals to 1. Okay, so this ratio. So now these are the values. So these two set is given when it arrives and what is the service time, and the rest you have to calculate based on the algorithm. So here we show the execution sequence using NAT chart. Okay, so NAT chart we show the execution sequence. This is the time increases in this direction. So here when at the time t equals to 0, this is t equals to 0, which process is there in the system? This is only process A. So the scheduling is trivial in this case. So process A will be scheduled here. Now, because it is, what kind of technique it is? It is non-preemptive type. So if it is non-preemptive type, once it is assigned the CPU, it will continue till completion. Doesn't matter what others are there and what other processes came and all this. So it will complete at time t equals to 3. So this is the completion time, TF. Okay. So this is the TF. So PA completes at 3. That's why we put here 3. Now at this point of time, after a process completes, the scheduling algorithm need to be triggered to find out which are the competing processes and which should be scheduled. So at time t equals to 3, which are the processes waiting in the system? Which are the processes waiting in the system after the completion of PA? Hello?
So just B.
Process?
B.
B only.
B, sir.
Because all the remaining processes they are not yet arrived. So B definitely, this is also trivial now. So we are using FCFS and we know the order in which they come. This is basically the order, and B trivially gets scheduled. And after, so it's scheduled, it is non-preemptive type. So you cannot take out this. So in any case, it will be utilizing the 6 units of CPU time and it will be completed at t equals to 9. So this is 9. Now when it was time t equals to 9, by the time you see the arrival of C, D and D, all of the 3 processes arrived, because the arrival time is at most 8. So at this point of time you have got 3 processes which are in the queue, C, D and D. So which one will be scheduled? It is trivial, it is FCFS. So first came the C, so C will be scheduled, and C, its service time is 4, so 4 units it will utilize again in a non-preemptive way. At t equals to 13 it will be complete, so it is 13. And then after that, at this point of time only D and E are remaining in the system, and from the strategy, D will be scheduled. It will be utilizing 5 units of time like this. We complete at 18, so that T finish is 18 here. And finally, P gets scheduled for 2 units of time and it gets completed at T equals to 20. So this is pretty trivial and simple enough to understand. So turnaround time, it will be the difference between the finish time and the arrival time. It is 3 minus 0, it is 3. This will be 9 minus 2, it will be 7. 13 minus 4, it will be 9, like this. So you can calculate this part also. and the mean value will be 8.6. And the normalized turnaround time, if we calculate the ratio of this with TS, this is the value and this is the mean value. Now, if we look into the performance, overall performance of this FCFS, what can be the comments on it? It is typically, it has got a lot of disadvantages. So what are the disadvantages of this? As you can see, if a long process gets scheduled somehow, so the long process is not going to be preempted. There is no way of preempting it, and it is not going to release the CPU also. So definitely the short processes behind a long process, uh, say they need to wait for a long time, and in fact the system favors the long processes. And at the same time, so this is a big problem. So you favor basically the long processes or the CPU bound process you can think of. But in the performance we found that there was something like they should be fair enough, this fairness criteria. So the fairness criteria is not basically fulfilled here, so this is a drawback. And at the same time you can see that another criteria was here is a predictability. Okay, from the user's perspective, the predictability. So predictability means what? If I look into the mean value, it is 8.6. So this 8.6, but you can see if I calculate the variance, even though I don't calculate the variance, but from the values itself, you see some values are 3, some values are 12, and the mean is 8. So there are typically there are some values which are much less than that of the mean. It's 3 and this 7, and 3 is like this. Okay, 3 and 12. So the variance is high. So there may be some so variance of what? Variance of the turnaround time. So some processes they feel that uh, they are uh, they are close to the mean, their turnaround time, and for some processes their uh, turnaround time is far beyond that mean value. Okay, so this is not good. So for few of the processes it is predictable, and for the many of the other processes this is unpredictable. So this is not good from the user's perspective. The user is not so the user will not feel good working in such a system using FCFS strategy. So although the strategy is very simple enough, there is no but will make the bad work. Okay, so the next strategy will be SPN or SJF. Can you hear me?
Yes, sir.
Can you hear me? Hello?
Sorry, your voice
Yes,
is
sir.
breaking.
I think you can hear me, no? So it's showing that is a bad quality of network. That's why I'm asking. Okay. I guess all of you can uh, listen to me. I mean, can hear me clearly. Anyway, so the next strategy is SPN or SJF. That is the shortest process next, or sometimes it is called the shortest job first. So process and job, they are basically the same terminology, more or less. And so this is a strategy. So this is also non-preemptive. So what it means, if you have got the time arrival times given here the same as the previous case, the service time also the same. So we take the same example, but the strategy differs. So if I again draw the NAT chart here, what we will see here, at t equals to 0 only PA is there, so PA gets scheduled, and because it is non-preemptive, it completes till it continues till completion. At this point of time only B is there, B waits. So B waits, trivially this gets scheduled and it completes till this point. Now when it was this much complete, you see at time t equals to 8, by the time you see I mean at this point of time C came, t equals to 4. At this point of time probably D came, process D came, and this point of time probably process E came. But none of this arrival of the processes would have impacted the running of the process B because it is preemptive, non-preemptive. Okay, so it completed, and only at this point of time the scheduling algorithm decides that it is CD and D, these three are waiting, and what the strategy says, it is shortest process next. So the process having the shortest what service time will be selected now. So service times are somehow hypothetically these are given, although it is not possible to know it prior, but let us assume that it is given, and in this case who are waiting for this CD and D with having 4 5 and 4 5 and 2. So definitely the one that is having the least uh, processing requirement will be scheduled. So basically it's the short processes which are favored straight away. And what is the objective of that? If I favor the short process, what will be the impact in the performance? What will be the impact? Which parameter will be impacted? System level parameter. If this is a strategy, shortest process next, shortest processes are favored. So which system level metric will be impacted? Which one? What will you maximize then?
The throughput will increase.
Throughput will increase. So first of all, it is not possible to satisfy or meet all the criteria, both user and system, as we mentioned. But in this way, just now earlier we found that the short processes are suffering. So now instantly there is a process that we can design which will favor the short processes, but you have to sacrifice the performance of the long processes. So you do one thing, you try to solve one end of the problem, you create another problem. So this way it is very difficult, although it is trivial, but it's difficult to meet all the criteria, desired criteria. So here if this P gets scheduled, so it will use for 2, and then all the processes arrive. So C and D, out of that C is 4, so it will be scheduled, and D like this. So this is trivial to write the NAT chart, and we show the finish time here. We show the process names, and the service times are shown here inside. And the length of this also is proportional to the service time. So these are the turnaround time, which is again the subtraction of this and this and this like this. Okay, and the turnaround time is 7.6. Earlier how much it was? 8.6. Now it is 7.6. So which one is better? Definitely this is better. It has reduced a little bit. So it is better, but it is again not the best, because you see still some processes like this one, uh, this has got a turnaround time 3, and the overall time mean turnaround time is 7.6. So it is still not been able to solve the problem, satisfy all of them. And as you can see, the normalized turnaround time also, it has reduced from 2.56 to 1.84. So things are improving, and as you can see overall the throughput has been much better. Okay, so but here the problem is the long process starves, long processes starves. There is a starvation problem. Okay, okay, so short processes are favored, and the service, and another major problem here is service time estimation. So service time is not always known, because so you have to estimate it, the whole uh, algorithm is based on the estimation of the or the knowledge of the service time, and that is somewhat hypothetical. So that is also a drawback. How can we know that? Okay, so then comes the preemptive version of shortest remaining time, or the service time. The point is, this is a preemptive version, and see the difference how the preemptive algorithms work. So if this is the turnaround, this is the arrival time 02468, and this is the service time which is 3642452. Both are the same for 5 processes, and now you have got this non-preempt. So it's sorry, this is preemptive. It should be preemptive. There's a mistake here. So this is preemptive, means when the preemption takes place. When this preemption takes place, or how frequent this scheduling algorithm will be executed. The previous two will be executed only when a process gets completed or terminated. Now in this case, how frequent do you expect the algorithm to execute, or in what event?
Sir, whenever a shorter job arrives, preemption will occur.
No, first of all, you don't know whether it is shorter or longer. The thing is, whenever a job arrives, you should take a chance to see that whether you can push this job, right?
Yes,
The
sir.
point, because whenever a new job comes, you don't know whether it is shorter or longer. Doesn't You don't know at all, but you should take a chance. So the thing is, the scheduling algorithm should run, and the scheduling, after running the scheduling algorithm, you may find that the process which is currently running should continue, because no other process has, even the new one that joined, is having a service time requirement less than this one, so it will continue. But you should uh, take into account that you should try to find that option. That's the point. And it can often happen that in that case a shorter job arrives compared to the one or the ones that are waiting, and in that case you forcefully preempt the running job. So now the frequency of this algorithm when it executes will now it increases. Okay, it's more. So here you can see at t equals to 0 only pa is there. Now for the first 3 time steps, what happened? After 2 time steps, what happened? Here process b came, but will it force a preemption? Definitely not, but the scheduling algorithm definitely got triggered here. When it got triggered, it found that the process a, how much time it is left now at this point of time?
1, sir.
1, but process b requires 6. So there's no point of stopping a. Let the a be complete, and like this. So there is a scheduling algorithm. The scheduling algorithm got executed, but no change was there in the scheduling status. But at this point of time 3, the process a got terminated, and then also it is very trivial because only b was there. So b got scheduled, and b was running. So after 1 unit of time, what happened? So that means at 4, who came? Process c came, and c has got a requirement of 4. So now here again the scheduling algorithm was executed, and it found that there are two competing processes. One, no matter what is status it was running, so it was b, whose remaining time is 5, and c, whose time requirement is 4 altogether. So definitely this is the shortest process, shortest or it's not the shortest process, it's the shortest remaining time, because it might happen that some process got preempted, and you should talk in terms of remaining times. That's why we call it as remaining time, not the shortest process next. Okay, the residual amount of service time that is remaining. So this p got scheduled, this c got scheduled, and c continued for 4 units of time. At point 8, at time equals to 8, what happens? Now by the time all these three, say b, d and e are ready, and definitely e has got the minimum shortest time, so e got scheduled here. After that b and d, so both are having the same requirement, service time requirement, remaining time. So anyone can be scheduled. Maybe the b got scheduled because it came fast, prior to d. So b got completed and d got completed. So this is one instance of preemptive scheduling, where a process like this b got preempted forcefully after just executing one time step, and later on it got scheduled here. Okay, there is a kind of preemption case, but the previous two was non-preemptive type. Now if we do this, we can still calculate the turnaround time by subtracting these two, this finish time from the arrival time from the finish time, and these are the values, and we see the value is 7.2. So earlier it was 7.6, so prior it was 8.6 FCFS, the mean value of the turnaround time. then it was 7.6, now it was 7.2. So things are improving. The mean value is getting reduced, and that is good for all the users. And we can see the turnaround time also is getting reduced from 2.56 to 1.84 to 1.54. But still you see some kind of variance is still there. So the variance is high but less than compared to FCFS and SPN. And service time estimation is but the here the also the problem is a long processes starve, because if there is a continuous pool of short processes that keep coming, so even though the scheduler is taking chances, but the long process will never be we will never get a chance, because its requirement or remaining time requirement is much more than the new short processes. So that is again in some sense favoring the short process, but this is, even though it is preemptive, it is favoring. In this non-preemptive also it is favoring the short processes. So both of these SPN, SJF or this SRT, these are favoring short processes, but SRT is a much it's a slight bit better in performance, because we have got a lesser mean value and a lesser normalized turnaround time. Okay, because of this preemption. So but the major implementation level issue is here is how we know the service time, the estimation of service time. This one, estimation of service time is non-trivial. Till now we just assume somehow, but this is not possible. I mean, we should have a fair estimation. So here there are several possibilities, I mean several possible ways we can estimate. A simple thing is, now say if I, so it can be based on history. Say you know that I often take some time to start the class, so often I delay the class. Now if we, can you guess that how much will be the delay to start the class in the next lecture? So in that case you say that okay, we'll look into the trend, like the last 2-3 classes he made say 2 minutes delay, sometimes 5 minutes delay, sometimes 8 minutes delay. So we take a average of that and we try to predict what will be the delay in the upcoming class. Okay, and at the same time you can also think of that, forget about the history, might be that he was taking long time, but recently he's not delaying a lot. So there is so in this estimation it is not possible to really guarantee the estimation is correct, but if you store the information of the amount of CPU time that the process utilized whenever it got scheduled earlier, so from that you can have a guess of how much time it will be requiring next. Okay, so when we talk about this, so this we include this we don't consider the forceful preemption case. So when the process was scheduled, then how long it used the CPU voluntarily, so that will give us a guess. And in case of IO bound jobs, so these short CPU bursts, the amount of time, if we can store it from that series of burst time, we can predict the next CPU time that is required by the process. So the idea is, if we have say the predicted value for the next CPU burst is say n plus 1, and n number of times it has already used the CPU, so tau n plus 1 equals to alpha tn plus 1 minus alpha tau n. So this means what? This alpha is basically it's a value which is in between 0 to 1. So if the value of alpha is higher, that means we are giving more weightage to the exact last value. Okay, and if the value of alpha is very less, then we are giving more weightage to the tau n. And tau n, what is tau n? Tau n is actually embedding the history of the of that waiting time in the previous time steps. So whether you are giving more weightage to the history or you are giving more weightage to the recent behavior, that you can actually have a choice of that using the value by choosing the value of alpha. So from this we can only estimate, and you can see that if this is the kind of behavior that it follows, the CPU burst at time t, and this is the guess. So if you have this kind of equation, you can try to catch up that in some form, and you can have, so this particular plot is actually an approximation of this continuous plot, and it is quite good enough to have an estimate like this. Okay, so there are different ways of implementing it. We can choose alpha equals to 0, as I mentioned. So in that case, it will be uh, weighing only the history, so it will give weightage to the history of the performance. If it is 1, that means it gives the entire weightage to the last time step what has happened, so it will ignore rest, like that. And if we expand this, it will be like this. So this is how uh, the service time requirement can be calculated, and we must know that this is non-trivial. And even though most of the scheduling algorithms depend on rely on the service time information or the remaining service time information, so calculation of this is non-trivial, and this is one way of estimating it based on the prior values from the right from the beginning when the process was allocated the CPU in multiple bursts. Is that fine, this part? So the last strategy that I'll talk about in this class is the HRRN, that is a non-preemptive strategy. So HRRN stands for highest response ratio next. Okay, so what is the response ratio? Response ratio is basically the ratio of the this is the turnaround time divided by the service time. So this is basically the normalized turnaround time. So what is the intuition behind this is, we definitely want to reduce the turnaround time, right? The mean turnaround time. We also would like to reduce the normalized turnaround time, because the normalized turnaround time, what is the ideal value of that for the processes? It should be 1, and if the processes are made to wait too long, then the values will shoot up and the mean value also will shoot up. So the idea is the strategy to minimize that normalized turnaround time is choose a process whose turnaround time at that particular point is maximum. So if you can schedule that process, so you can assume that or you can probably guarantee that the overall turnaround time, uh, I mean that is the best way through which you can try to reduce the overall turnaround time, right? So that is the strategy. So you really don't know what is going to happen next because it's a non-preemptive strategy, but you don't know the arrival of the other processes uh, that are about to arrive, but that's the base strategy that you can take at that point of time. Okay, so the basic intuition is the normalized turnaround time need to be reduced. So whenever we need to take a decision, so when we need to take a decision, the algorithm is triggered each time a running process terminates, because it is non-preemptive. So whenever a process terminates, the remaining processes which are waiting, it will try to compute the response ratio of each process, and it will select the process with the highest response ratio, and it will schedule it. So that's a simple strategy. So if I just execute this, so this process A requires 3 units of time, and you cannot interrupt, you cannot preempt, you need not have to run the algorithm also in between. So at time t equals to 3, you run the algorithm, and what you find is B is only waiting. So what is the, so I have not calculated. So B is only waiting. So it's you can calculate its response ratio. I have not calculated. I will make the change, but this is trivial. So this will be only, scheduled. Ignore this part. So B is scheduled, and once B is scheduled, B will be utilizing all the 6 units of time. And after the completion of B, now there are 3 processes C, D, and E. And if you calculate the response ratio, the values are this 9 by 4, 8 by 5, and 9 by 2. How it appears? what should be the value of, what will be the response ratio of C? How we get this 9? This is TS plus TW for the C at 9, at time t equals to 9. This C, what is the waiting, what is the amount of waiting time for this? How much time it waited?
So 5.
Because it arrived at 4 and it is now at time 9, so it's waited for 5 units of time. So 5 plus its service time is 4, so that's why it becomes 9 divided by 4, the service time. Okay, for D you see D arrived at time unit 6, now it is 3 units that elapsed, so it is 3 plus this S 8 divided by 5. For E it just arrived the last time step, so one unit of waiting time plus 2. For E it will be, how much? 1 plus 1 plus 2, it's 3 by 2, no? This is mistaken. Okay, I'll change these values. So eventually you will find that which one will have the highest response time? Highest response time is C, and C gets scheduled because it has got, you see, this is 4 and is already waited for 9. So if you allow it to wait for long, so this process is effectively is going to increase the overall mean of the normalized turnaround time. So this should be immediately scheduled. After this gets completed in a non-preemptive fashion, then D and E are remaining. So D and D you can calculate accordingly. And then which one is higher? E is higher probably because it has only 2 units of service time. It is already waited for 7 units. So this gets scheduled. So I think now the calculations are correct. 7 means it is say it has arrived at 8. So 5 plus 2, 7 divided by 2. Okay. So definitely at the end you will have only the D. So D waits, so D is scheduled. So these two has got the same type of problem. You have to make assumptions on the service time of the process, which is something hypothetical, and in this case the long process, so the long process still then, so just remove this. So long processes may not have to starve always, because in this case you see that if a long process waits for long, then what is going to happen? Its turnaround time will be high, and in that case it will not need to starve. So at some point of time it has got a mechanism that if you may be a long process, and if your waiting time is proportional to your service time, then definitely you will beat all the small short processes and you might get a chance to get scheduled. So this is how in this particular strategy, dynamically based on your waiting time and based on the comparative waiting time compared to the service time, processes are often get scheduled no matter where they are originally a CPU bound or a IO bound job. Okay, so this is one particular strategy where we see that there is some kind of dynamics where the waiting time is considered in the scheduling. No other prior algorithms did use that, right? Because waiting time is a critical thing. So if you're waiting for too long, you should be given a chance. That's the idea. So this is one way of doing that, and the rest of the strategies we'll consider in the next class. Just to fix a point that there are other kind of uh, other ways of implementing scheduling, that is we form different queues, and say in this case you have got different types of queues. So as in case of banks, you may have a say queue for elderly persons, queue for say maybe staffs, and then queue for students, like that. So the highest priority is for the elderly persons, then the staff and officers, and maybe institute staffs, and then the students, and then the outsiders, say for example. So if this queue is empty, only then the users of this queue will be served, and only then like this. So this way it can be a multi-level queue. Different levels of queue are defined, and the process when it arrives in the system, the nature of the process is first identified. It may be a system process, interactive editing process, batch process, student process, like this. So definitely the highest priority is towards the upward queues, and accordingly, so the point is there is no switching between the queues. So once you are a student, you should always enter in this queue like this. Even if you are waiting for long, doesn't matter. So this is in some sense simple enough. The strategies to define the queues are important and non-trivial, but there is no switching between the queues. So this is bad. In a multi-level feedback queue, this is better than that, and I think we'll talk about it later on in the next class. So this round robin and different type of queue based scheduling, we'll talk about it in the next class, followed by the fair share scheduling, which is actually implemented in the Linux type systems. Okay, so this much for this particular class. So the scheduling is pretty a simple topic to understand, and in the next class we talk about fair share scheduling, and also we'll talk about another so some codes, there is a nice value. The nice, by tuning the nice, a process can alter its priority. Okay, scheduling priority, and in fact a process can reduce its scheduling priority, and definitely not, it cannot upgrade or increase it. So we'll see the impact of it, and we can see the effect that it is happening by writing a code. Okay, so if you have any questions, you can ask. Let me stop the recording.